Good afternoon. Okay, sorry for the delay. Can everybody hear me? Hear my we're on. So this is the third, I think, Hellenic Association for Aerosol Research Seminar that we have today and the talk today is by Manos Manousakas. Manos has been doing his research. He received his degree from Patras, the University of Patras, Department of Chemistry, and he has a PhD awarded to him on environmental analysis by the Chemistry Department of Patras University in 2014. He has more than 10 years experience in atmospheric science and environmental analysis. And he has focused on the source apportionment of aerosol particles in the atmosphere. He has been a tutor and organizer of several workshops on this topic, and also contributed to the European Guide on Air Pollution Source Apportionment Receptor Models. He is working on these techniques using data from chemical composition from in situ aerosol measurements, and this is relevant to the topic of his presentation today. So, Manos, you have the floor.
Okay. Thank you, Costa. Let me share my screen first. Do you see the right screen or the presentation mode?
Yes, Manos. Yes.
Okay, great. Cool. Thank you very much. Okay, so thanks, Kostas, for the introduction. My name is Manos. I currently work at NCSR Demokritos, but the presentation that I'm going to show you today includes mostly results from my previous position at Paul Cerar Institute in Switzerland. I moved back to Greece fairly recently, so there are some things we worked while I was at PSI, and we're still working at the moment. So in this presentation, I'm going to talk about source identification strategies, mostly based on receptor models. And
a small interruption.
Okay. Yes.
Manos, small interruption. Maybe on the display settings you can choose either to duplicate the screen so that we have your screen at full screen mode.
Is it now okay?
Now it is okay, I think.
Great. So in the presentation, I'm going to talk a bit. I'm going to try to cover the entire spectrum. So I'm going to talk initially some very basic stuff about source apportionment using receptor models, but not for too long. Then I'm going to discuss a bit some techniques we implemented for online data source apportionment at PSI, then present you a new solver that in the future maybe can be used, and then some other studies and some connection of source apportionment to health related metrics. So without further ado, let's start. So as we all know, PM vary in composition a lot depending on the area that we collected them from or we studied them. And this happens because PM are emitted for a variety of sources, and regarding of what type of sources they come from, then the composition has to be different. And here we have two examples of that, two overview studies. One includes mostly includes only European countries, the other one mostly European countries. And this study is focused on the ACSM data. So we have ions and we have the organics, and then the other one is more the classical chemical composition data, so ECOC elements and so on. But the thing that we can see easily is that the composition of PM is very variant, and this is highly related to the sources and the processes they're formed from. So what is source apportionment? Source apportionment, if we want to describe it in just a couple of sentences, is the practice of deriving information about pollution sources and how much they emit from air pollution data. What does that mean in practice? It means that we get the chemical composition information from PM, and then we use that information to go back and identify the sources. And of course, the sources that emit PM can be very variant, and they can include a high number of different processes. And those processes can be either anthropogenic or they can be natural. So what that practically means, it means that when we go to a certain area and we measure PM, those PM, they were not there, they come from certain sources. So we have a certain sources of PM in an area. Each one of them has a certain contribution. If we add all contributions together, what we end up with is the total PM mass. It doesn't matter which fraction of PM we're talking about, this is how it goes. So source apportionment is practically going the other way. And then from information about PM, we tend to go back and we identify the sources and how much they emit. And how we do that? We do that because the different sources that we have in an area, the PM that they emit, they tend to have different chemical compositions. Sometimes it might be similar, but usually there is always some difference in the chemical composition of PM when they emit it from different sources. And we are using this difference in the chemical composition of PM to categorize them and analyze them and be able to identify the sources. So practically how this works from a simpler point of view, what we have is the chemical composition data for the PM, and then we're using certain type of models that what they are doing practically is that they are checking the correlation, the intercorrelation between the different elements. And by checking this correlation, they group the elements together in what we refer to as factors. And then we read the chemical composition of these factors, and then we assign those factors to sources. Of course, source apportionment is a very, very broad term. It includes many different techniques. Those techniques can be very, very simple techniques like chemical reconstruction, for example, where we just account for some missing mass and then we add the mass together and then we end up to PM. To complicated mathematical models to receptor models. So we have emission inventories, chemical reconstruction, inverse modeling, artificial neural networks, chemical transfer models, but my presentation will be mostly focused on the receptor models. So what are the receptor models? The receptor models, first of all, are focused on the behavior of the ambient environment at the point of impact. What that means is that when we apply a receptor model, we need information from a certain region, and the results we are going to get are specified for this certain region. Because to apply a receptor model, we need to do some sampling, and we need to have information about the chemical composition of PM. This can be different things. This can be offline sampling, sampling and then offline analysis or online instruments. It doesn't matter for as long as we have chemical information about the composition of PM. So receptor models, they use real measurements. It's not a modeling process. We need to actually
Τι έγινε τώρα?
Πάρω ένα τηλέφωνο και εγώ τον Κώστα να δούμε τι έγινε, μάλλον.
Διακοπή ίντερνετ.
Εγώ νόμιζα ότι απλά χάθηκε το δικό.
Και εγώ αυτό νόμιζα, αλλά τελικά... οκ, τέλεια, να το ο Μάνος.
Okay, so now I'm back. I'm very sorry, but we have some internet connection problems in the institute. hear me now? We have some internet problems in the lab, so I now connected from my cell phone practically. But I don't know. Can you hear me?
Yes, now.
Yes, yes.
Yeah.
Okay, let's hope that was the last time this happened. I sincerely apologize. I'm gonna switch off my camera, hopefully making things a bit smoother. And let's hope that this won't happen again. Okay. Okay. Again, I apologize. Regarding receptor models, okay. You still hear me, right?
Yes.
Yes.
Okay, great. Because cool. We can use receptor models only with pollutants that they have various constituents, which means that if we do not chemical information that we can use to characterize the different emission from different sources, then we do not have simply what it is necessary to apply this type of models. And we can combine the output with whatever other type of models we can use. So receptor models, regardless of the type, they all use the same mass balance equation, and all of them are using the same fundamental principle, which is that the mass is conserved. So as we discussed at the beginning, the sum of the sources they produce part of PM mass, and summing the PM mass, we have the entire PM mass. We have, this is the main mass balance equation. So what the receptor models does is that they decompose the matrix that has the composition of PM into two smaller matrices, one that it has the F, which is the factor profiles, and Z, which is the factor contributions. So practically this matrix X is the which represent the different sources, and the other one has the factor contributions, which represent the overall contribution of PM. And this is not just the overall contribution of PM. This can be the daily contribution of the sources of PM. So X, as we discussed, is the chemical composition dataset. So to apply receptor model, we need some type of chemical composition dataset, like this one, for example, here. And this can come from any instrument, and it can include any component of PM. It can be based on the organics. It can be a combination of different instruments or techniques. So whatever refers to information about the chemical composition of PM can be used for receptor modeling. And receptor models, to solve this equation, there are different approaches. And here I'm showing you how PMF is actually solving this equation to get the results. And to do that, PMF is minimizing this function Q. So practically what it does is that it measures the residuals, which is the difference between the modeling value and the real value, scaled by the uncertainty, and the sum of these residuals. In principle, the smaller that is, the better the modeling. So this is how PMF works. So those was a bit introductory stuff for the people that maybe were not very familiar with this concept. And now I'm gonna discuss a bit more about different data. So what we are doing at PSI, because we were applying source apportionment methodologies with different type of data, we categorized these approaches based on the type of data we're using. So I'm gonna just show you the categories we were, as we have defined them, so we can easily then understand which category refers to which results. So first we have the classical offline source apportionment, which includes the most commonly used approach, which means that we first sample some samples in whatever receptor we choose, and then we take those samples and we apply offline analytical techniques for different components. So we can have information about ECOC, we can have ions from ion chromatography, we can have the elements from XRF, ICP-MS, or whatever other technique. We can have PAHs or whatever other technique we can apply into filters collected. And then someone needs to collect all this data, needs to treat all this data, and then apply some source apportionment model, and then we can get information about the sources and the contribution. Then we have other different type of offline measurements. In this case, we can apply different analytical approaches, not, let's say, what we refer to as the classical ones. We can apply more complicated offline approaches like AMS or EASY. And in this case, we can have a different type of chemical information that we can use for source apportionment. Then we have another category. This is a bit more recent than the other ones. So we have the online instrumentation. So this approach does not include sampling. So we have online instruments. We can have different type of online instruments like the EXACT that measures elements, the ACSM that provides information about the inorganic ions and the organics, and the ethalometer for black carbon. And then we need a user that collects all this information and finds a way to utilize them appropriately to get to source apportionment. The advantage in this case is that we do not need sampling and that we have high time resolution. And then we have advanced online technologies. So instead of having this type of instrumentation, we can have other type of online instrumentation that provide, for example, near molecular information, like the EASY, or we can have an AMS. And again, the procedure is the same. Someone needs to collect the data, treat the data, and then do the source apportionment. And finally, we have some other approaches. We call them real-time. And those approaches, they start gaining more and more ground lately. So in this case, what we have is, again, we need to have online instrumentation, of course, instrumentation that provides the data in a near real-time manner, in a high time resolution. And then we have a specific real-time source apportionment software that takes this data and provides the source contributions and sources without the interference of any user. And in theory, this can be done in a near real-time manner. Okay. So now I'm gonna show you some examples of those different approaches. And the first, I'm gonna talk to you about the online source apportionment application, and I'm gonna be focused more on the EXACT data, since this instrument is not so new, but it's not have been used widely in the last years, in the recent years, and maybe there's still some ground of discussion on how to best implement and how to best utilize the data that they come from this instrument. The EXACT is an automated source apportionment, an automated XRF instrument, which means that it does the sampling in whichever PM fraction we select. We can do it PM10, PM2.5, PM1, or TSP. And then after the sampling, that it also analyzes the sample for using XRF analysis, and then it provides the elemental composition of PM. And this is done in a near real-time manner, so we can select the resolution of the instrument from a few minutes to a few hours, and the instrument then, after sampling, does the analysis automatically, and then it provides us the result. And another thing that we can use with the EXACT is that we can use a changing inlet, which is a system that can switch from one PM fraction to the other. So we do not have continuous collection of just one PM fraction, but we can switch to different PM fractions. Okay. So the switching inlet was first designed at PSI, but in the recent year, this design was adapted by Cooper, and it's now commercially available for anyone to buy from the manufacturer of the exact itself. So practically, it's very simple in its approach. So we have two lines with two valves, and then we have a straight line that goes to the PM10 line, and then we have another line that bypasses and goes through a cyclone, a PM2.5 cyclone, and then one valve closes, the other valve opens, and then 1 hour we can have PM10 sampling, the other where we can have PM2.5 sampling. Okay. So some advantages and disadvantages of the switching inlet. Information about two size fraction using a single instrument. So we also have reduced measurement uncertainties compared to having, for example, collocated instruments, because all the calibration, everything refers to just a single instrument and not two different instruments, which usually makes the uncertainty lower. And it is possible to estimate the core fraction of PM, but because the measurement is, as I said, asynchronous, so we have 1 hour, one fraction, the other hour, the next fraction. If we want to estimate the course fraction, then we need to find a way to interpolate the data, so we have synchronous data. So some disadvantages is that if we're using the system, then we have 50% of each size fraction for the 24 hours. So we have 12 hours, one size fraction, 12 hours, another. So we do not have full continuous data. The data sets are alternating. And if we have spiky time series, or if we have events that mostly affect one size fraction or the other, we are going to lose information. And if we check the average in the long term, then the average might not be the same, since we do not have continuously the same size fraction. Okay. So regarding the uncertainties, there was a study done by Markus Fugger at 2020. He practically estimated the difference in the average when we're using the alternative system and we're not using the alternative system. And practically, what we can see here is that the coarser fraction, the elements that are mostly on the coarser fraction, the average can change a lot, because we tend to go from PM2.5 to PM10, while the elements that are mostly on PM2.5 fraction, they're not so much affected. But in general, the uncertainty or the change in the average is not that high. So let's say that we do have the exact and we do have a changing inlet, then the question is how it is best to use the data to get as much information out of them as possible. And we could report them as continuous time series. So we can report as a data set that has alternating PM2.5 and PM10 data. So usually that's continuous, but of course the size fraction will be alternating. We can report it as independent time series, so PM2.5, PM10, with gaps of 1 hour, because the sampling is alternating. And of course, the uncertainty needs to be estimated differently regarding of how we treat them. Or we could, in theory, report them as continuous time series, but then we need to find a way to do interpolation and fill the changing inlet. And then the uncertainty estimation in this case is not continuous for the entire data set, but it's different, because then in the same data set, we have real measurements and we have interpolated measurements with differently for each point. Okay, so in PSI, we had a large data set of exact data. The results are presented in the paper that it's shown here. So we had 1 year data practically for the exact, and we had the changing inlet. So we had 8,000 points in totals, 4,000 points per size fraction. One-year data coverage, 4 seasons, and so on, information out of it. So we are practically doing some tests. First, we use the data as one single data set. Then we separate it to PM2.5 and PM10. But what we end up doing is that we end up interpolating the different data sets to PM2.5 and PM10, and then we use those data sets to estimate the coarse fraction. And to do that, the interpolation was easy. We just did a linear interpolation. What was a bit tricky is to find a way to estimate the uncertainty of the interpolated points. And Costa, you need to mute. Okay. Cool. And what we end up doing is that we did the interpolation, which was a linear interpolation, and then what we did is we found a way to estimate the uncertainty of the interpolated points based on the PM2.5 and PM10 ratio. And after doing that, we use the data as a PM2.5 PM coarse dataset. So we have a PM2.5 dataset, and then we have the PM coarse used and combined like that, and used as a single dataset. And the advantage in this case was that we do not only had the information, the high time resolution information about the elements that the model could use, but we also have to get the sources. And I mean, this is how we defined it in the model. So we defined the 2 different classes, but this is a technicality. I mean, if you're interested, we can discuss later. And the uncertainty of PM2.5 was estimated like that, and the uncertainty of PM coarse was the combined uncertainty of PM10 and PM2.5. And what was the benefit by using a dataset that has PM2.5 and PM coarse instead of using one size fraction or the other? Is that because of the size aggregated information, we were able to identify more sources than what we could otherwise. And we end up having 13 sources, and we could identify different, for example, different traffic processes like low-duty vehicles, heavy-duty vehicles, mostly based on the size aggregation, also local tasks to transport the dust and so on. And the way we used to evaluate these results was to compare those results to external data and also check the elemental ratios according to what is reported in bibliography for sources that we know that we could check. For example, fireworks, we check the potassium to sulfur ratio. It was very close with bibliography. And for other elements like transported dust, we checked, we coupled that to long-range statistical trajectory methods. And for salt, the same. So here we can check the contributions as time series. And for example, another interesting thing that we can also discuss later if you want is how to treat very high intensity events that they're very short lasting, like fireworks and so on, that tend to mix a lot the solution. For example, you see here the time series that we have some spikes, huge spikes. These ones that they refer to the firework events that even though they are just for a few hours, they have a super high contribution during this time. And even those just few points, they complicate source apportionment quite a lot. So, and here we see the diurnal variation, which is something that we can also use and we can also check when we have high time resolution data. Okay, and now I'm moving to the real-time source apportionment application. So for the real-time, first, what we need to have is real-time instruments or near real-time instruments. And for that, we were using what we refer to as the AXA setup, which is the exact, ethalometer and the ACSM. That is produced anyway automatically, and we collect them in the acquisition PC, and then we can load those data automatically to a software that treats this data, runs them into source apportionment, and provides a pie chart of source contribution without any interference from a user. But of course, things are never that simple, because to get to do that, we need to first have the real-time source apportionment software, the real-time source support. It can provide good results. And to do that, we need to insert some information to the software, and we need to insert the number of sources, and we need to also have the source profile. And of course, if we use cloud services, then the software doesn't have to be in the station that we're actually doing the measurement, be anywhere. In Switzerland, for example, or can you hear me?
Yes,
I have no idea where was the point that you lost me. I'm sorry.
just a few seconds ago.
Okay, that's good. So I was in real-time source apportionment already, right?
Yes, yes.
Yeah,
Okay,
yeah.
that's good. Again, I'm really sorry. I mean, this is a huge problem we have. Oh, let me then search my screen again. Okay, hopefully you can see the screen and also hear me. Is it okay?
Yes.
Cool. Okay. So why we use this AXA setup, the ACSM, the exact, and the ethalometer? So each of the instruments, as we discussed before, provides information about different components of PM. So the ACSM provides information about the organics and the inorganic ions, exact about the elements, and the black carbon and the ethalometer about the black carbon. All three of them, they do automated data processing. And if we add this information together, what we end up with is practically most of the PM maps. So the way we implemented real-time source apportionment, and the results that I'm showing you in this methodology that I'm describing is how we did it in a specific project in China. Doesn't mean that it cannot be done differently, or it will not be done differently in the future. So what we did, because in this specific project, we were preparing a software that in theory should have been used by environmental agencies. So from people that they do not have extended experience in source apportionment techniques. So we wanted something that was very robust. And the way we end up doing it is that we did practically 3 source apportionment for the 3 different fractions. So we had one done for the organics, one done for the elements, and for black carbon, so BC liquid and BC solid fuel. And then the software took this information from the different source apportionment and recombined them into a single pie chart, having the information about the primary sources and also the information about the secondary components. And the project that I was referring to before is this one described here. So we had a project in China that took place in 6 Chinese cities. So Xi'an, Chongqing, Beijing, Langfang, Wuhan, and Shijiazhuan. And in each city, we had 6 months of measurements. So the process was that we did, first of all, the sampling campaigns. Then we took the information about from those 3 instruments and we did an online source apportionment analysis, so an optimized source apportionment analysis. And we use this information from this optimized source apportionment analysis to set up the real-time model. And then we test the real-time model, and we also test it in simulation. So how well it would have performed if it was used real-time. And we also tested it in actual real-time conditions. So for the optimized source apportionment runs, we used SOFI by Datalistica, and we followed the procedure described in this paper by Gang et al. This is a paper that comes from a European project from Cost Colossal. So within this project, there was developed a harmonized source apportionment approach. So we followed this source apportionment approach, which included seasonal pre-tests, bootstrap runs, and also rolling MF and criteria-based selection. So we tried to implement all the tools that are available at the moment to do a comprehensive source apportionment. And by doing that, we got the source profiles and that we used to set up the real-time model. So after we tested the real-time model, then we end up having this pie chart for this series. The advantage of this methodology is that it's very robust because, again, real-time is different than the classical approach, because in real-time, consistency and robustness is super important because it is meant to work unattended. And if we have very complicated approaches, then it is quite easy that the model gives us wrong data that we cannot realize until quite later. So the model was providing information about the primary sources, whether those were from organic part or for the inorganic part, and also the concentration of the inorganic components of PM. And then the question is how well this real-time works. And the answer is, if it is set up properly, then it works quite well. So here we can see the comparison of the real-time source apportionment results compared to the optimized source apportionment approach that we did. And of course, this is the best case scenario because we did an optimization prior to the real-time application. So if you do not do that, of course, it's not so easy to get such good results. And also the campaigns were not long-term. So we do not know how this is going to behave if we apply the same, for example, source profiles for a year or 2. So it is a best case, but even in this case, we see that if set up properly, then the real-time can work. So we see some outliers, for example, here in the biomass, and then these outliers, we found out that they represent like firework events that the real-time model misinterpreted for biomass. And this is the problem for the real-time, that we need to set it more or less for a base case or for an average case. And sources that are not expected, then it's not so easy to set it up for. So may have some outliers, but even in this case, the performance is still reasonable. So this is practically shows what I described, that real-time has its limitations because these events, they are not so easily modeled. So for example, fireworks, it's not so easy to include in the real-time source apportionment model. And the other thing that we had during the studies, that we had 2 huge dust events that, again, if you're doing the analysis offline, we could split into 2 different factors, the dust storm and local dust. But the real-time model is not, it's not possible to be set to get these differences. We also tested this methodology in India to see whether it is possible to implement elsewhere. And the result was also quite robust, but we have not tested it for the full access setup, just for the exact. And of course, when you use it for one instrument rather than three, it's easier. And it's also not limited. The technique is not limited to be used by all three instruments, but you can separate which one you want to use, and you can use 1, 2, or 3 at the same time. Of course, when you use it for single instruments, the information is limited, but the application is there. Okay, so what I showed you before was more or less ways of utilizing tools that we already had available for some years, but source apportionment also evolves, and the main reason, the main way this can evolve is that if we get new solvers. So I'm going to describe you a bit here a new solver. The solver, this one is called BAMF, and it includes Bayesian matrix factorization. So practically the difference is, as you see here, in PMF, the goal is to optimize Q, which practically to optimize the reconstruction of the data, so to minimize the residuals. But the problem, let's say, in PMF is that it does not use time information. And this could be an advantage if it was done, because atmospheric measurements, they have strong temporal autocorrelation. And here we can see an example of different PM components and how the correlation with this is hours and this is the correlation. So we see that the measurements are highly correlated even if we go further in time. So this model, this BAMF, it is a probabilistic matrix factorization method, but that accounts for autocorrelation. So what it means is that it tries to minimize the residuals, same way as PMF does, but it also includes a penalty for deviation from the autocorrelation in G. So it uses two different parameters to get to the solution. I'm not going to describe you the math a lot. I invite you to refer to the paper with everything is fully described. I'm just going to show you very briefly some of the results of this model. And to evaluate this model, we use two different synthetic data sets. One was replicating or mimicking observations from Beijing, which included high concentrations and low correlated time series. And the other, practically a synthetic data set that replicated measurements from Zurich, where we had something that is closely resembling measurements in European cities with low concentration and high correlation to time series. And okay, so those are the results of the evaluation. So here you see is BAMF. The pink line is BAMF 0, which is the same solver as BAMF, but without taking account the autocorrelation. The other one is PMF, and the dust black line is the truth, because we had a synthetic data set, so we knew the truth. BAMF had better factorization performance in F and G, that models that did not account for autocorrelation. Oh, I forgot to mention that this comparison refers to the simulated megacity source apportionment, so the simulated Beijing data. So as you see, it's slightly better, for example, in HOA, but generally speaking, in this particular scenario, all models did quite well. So the differences were low between the models. So now we move to the data from the European city, so the data simulating Zurich practically. And in this case, because we had low concentration and the high correlation between the emissions from the different sources, so then it starts to get tricky for all models. And I forgot to mention that all the runs that I'm showing you here was fully unconstrained. So we used PMF unconstrained, not the way that we usually do constraining some factors, right? So if we check here, we see that BAMF would get the time variation of the sources, but of course it had a large difference in the absolute values. But we see that, for example, PMF was not able to distinguish between the SOA and actually provided two sources that were exactly the same twice. So in this case, BAMF did better in separating the sources, but to get the absolute concentration, none of the model did good. And then the other question is how the model would behave if we do not know how many sources we have and we use a different number of sources. So for example, here we had an optimum number of sources that were 4, and we used 5 to see how the models behave. And then again, we see that, of course, if we ask the model to produce 5 sources, the model will produce 5 sources, but we see that BAMF produced something that was totally unreasonable, which means that it was easier for a user to identify that something's wrong with the modeling. For the extra sources, what PMF did is actually it split it one sources into 2, while BAMF created a new source that was totally unreasonable. So this was easier to spot for a non-experienced user. Of course, again, every example that I show you here, it is fully unconstrained. We also include in the paper results of constraining the data and how each model performs when we fully constrain and we partially constrain the results. So you can refer to it to the paper. But generally speaking, as an overall, let's say, message is that this kind of tools, Bayesian matrix factorization tools, could be something that we can use in the future, and hopefully we will use in the future. They have certain advantages over more conventional methods like PMF, but of course they do not come without disadvantages as well. So generally speaking, this seems to be a nice complementary method to what we already have. And under certain cases, this also could perform quite well. And now I'm briefly going to show you some results, just some examples of other studies from PSI that fall within the categories that I described to you in the beginning. So this study published in Atmospheric Environment, this is an advanced offline source apportionment. So practically the sources of organic aerosol in Milan were quantified based on samples that were collected in 2013. So practically what was done here is that we took samples from 2013 and we analyzed them offline with an AMS, and then we use these AMS data to do a source apportionment of the organic fraction of PM. And this is the biggest advantage of this approach, that you can use filters that have been collected in the past and you do not have to go back and do a new analysis. Those results refer to the water-soluble part of OA. And we can see briefly the results here. And so the main finding of the study is that BBOA was the main source of Milan during winter. And this was attributed to inefficient combustion conditions that increased the BBOA contribution to oil. And another important thing about source apportionment is that we start now more and more not to use the results not to just use the results from source apportionment in the studies, but then start to combining those results to health effects. And the main way to do that is to combine source apportionment results to oxidative potential measurements. And we can do that offline, and we can do that also online. So, for example, in this study, we used the data from the source apportionment analysis we did in the Chinese project that I referred to before. And we also had, during the campaigns, we also had an oxidative potential instrument, online instrument installed. And then practically what we did is that we took the source contributions that come from the real-time model and the applications we did, and we coupled them with OP, the online OP we got from the online instrument. And of course, this combination was done by regression analysis. And for the regression analysis to work, then the time series of the sources don't need to be very correlated, otherwise it doesn't work properly. So we had to group the different sources into group categories. So we practically grouped them in primary sources, secondary sources, fireworks and dust to account for these events. And as you see here, the main OP sources were mostly the secondary OA sources. And what is interesting that when we had the events, the fireworks and the dust, then the fireworks were quite important to OP. And the other thing that was quite interesting is that the dust, even though during normal conditions practically does not provide any OP, when the concentration is very high, then because it is very high per volume, it contributes quite significantly. But please have in mind that the 2 dust events that we got during the campaigns, it was the biggest one recorded in the last 20 years in China. So this is why the OP was so high for dust, which means that even sources that they contribute low to OP, if the concentration is high, then of course, those are not negligible anymore. And finally, the link between health and OP, we can do it online, as I showed you before, but we also can do it offline. This is another publication. This is actually super recent. I mean, it was published online yesterday. So in this one, what we did is that we did the advanced offline. So instead of using the AMS, we use the EASY, which provides near molecular level specification of OA. And then we did different OP assays to evaluate the oxidative potential. And this was done in 5 cities in India. And the main goal was to find sources that mostly contribute to OP, plus how this is affected in a temperature. So how the different cities are affected by different sources and how the sources affect OP. So the main findings were that in Delhi, we had ammonium chloride and organic aerosols from traffic exhaust that were mostly affecting OP. And outside Delhi, so in the more in the less populated areas, then we had biomass burning being the main driver. And here you can see how the different components contribute to OP. So here we have the inorganics. The inorganics, even though they had concentration, they had no contribution to OP. Then we have the cold season OA, which had the highest contribution. So this is secondary OAs that mostly come from biomass burning. Then we have urban OA, so secondary organic aerosols coming from traffic-related processes, the BBOA, primary BBOA, then the primary burning, and the HOA. And we also checked how some of the metals contribute to OP, and you see that some of the metals, they had quite large contribution to OP, even though the concentration was super low. Okay, so some conclusions and some things to look forward to regarding some developments. So source apportionment techniques are versatile tools that can be applied using data from many different analytical techniques. The type of techniques we're using for source apportionment can be suited to the goals of the study, so we can use whatever we think regarding of what we want to achieve. Online instrumentation that we have available now allow us to do real-time, to implement real-time approaches. And of course, the results can link to OP either offline or online, and then we can, let's say, directly link source apportionment results to health effects. And some things that are coming soon from work that is already done and should be available within the year, I would say. So the things that we are working on is now some methods for optimizing real-time source apportionment configuration based on single particle analysis. There is a new solver coming this was developed by Pentti Patero. We are testing it at the moment. This is called RPMF, rotational PMF, and the main advantage is that the computational time is extremely smaller compared to ME2. We're also evaluating some new approaches to use the real-time source apportionment. Some other interesting data that will also be coming soon is the source apportionment of secondary organic aerosols in China using near molecular level information, and also implementation of real-time source apportionment using the access data, but not, let's say, in a research way, but also in monitoring stations, so in a more, let's say, a day-to-day way, an unattended way, and see how this behave in long term. So that's it from me. Thanks a lot for your attention, and I would happy to take any questions you may have. And again, I really apologize for all the interruptions.
Thank you very much, Mano, for the very interesting presentation covering so many experimental data and simulation tools. It was very interesting. Thank you very much. May I begin with a small technical question?
Yes, of course.
I would like to know, so this instrument, this XRF instrument that you have, it's measuring online the aerosol directly. It's not on a, that it is deposited on a substrate and the measurement is implemented there? Or did I not?
No, it is a
understand?
substrate. It is a substrate. Yes, you were right. So you practically have a Teflon tape. It works quite similar to an ethalometer, let's say, right? So you have a tape, then it moves. You have one point at the sample on the tape, then the tape moves to the analyze part of XRF. So you have the XRF on this spot, and at the same time that you have the analysis on this spot, then the other spot, the next spot, is collected in the sampling component of the instruments. Typically, it works similar to an ethalometer. So you have a tape that it moves, and you have the sample on the tape. The difference is that you have a Teflon tape instead of a quartz tape that you have in the ethalometer. And then each sample point, each spot is separate. So you do not have, for 2 hours, the spot being sampled twice. So its sampling is new. So you don't have the artifacts of double sampling, or I don't know how to call it.
Okay, that's very interesting. Thank you. So just to understand, so do you believe that it is it has, let's say, the same this XRF, the XRF technique would have, like, let's say, the same resolution like the ICP implemented, or you believe it's just your feeling?
Well, there are studies that compare to when it first came out. There were some studies comparing the results of the exact to ICP, and the agreement was very good. I mean, for some elements, ICP would be superior for sure, but generally speaking, this is a really robust instrument that can provide information about elements with low concentrations, like for example, arsenic, lead. So yeah, I would expect that for low concentrations, ICP would outperform the exact, but for a day-to-day operation, I think this is extremely good.
Okay, thank you very much, Mano, and congratulations
Most
again.
welcome. Thank you.
So are there any other questions for Manos from the audience?
Michael here. How easy is to implement the Bayesian technique?
Not so easy. And that's the reason, the main reason we have not heard more about it so far, is that at the moment it's super hard. Practically Anton and maybe Caspar and maybe me can do it. So at the moment it is in let's say in a research stage at the moment. So it's not easy for anyone to implement. But the goal is that this will change, that there will be a proper, let's say, software that anyone can use. And then, of course, this can be used also in SOFI. This is the plan, but at the moment it's not so easy. It's possible, but it's not easy. You're referring to the practical one, Michael, right?
I'm asking in PMF, the good thing about PMF is that if you input data, you get something out. And most of the times, it may not be 100% accurate. There might be problems, but at least you get, for instance, the factors right. Most of the times I've tried it, even if I haven't checked my uncertainties properly, even if there were problems with the data, the factors that I would get wouldn't change much after I refine, let's say.
What type of data are you referring to?
Filtered data. Mostly I have filtered data in my mind.
Filter
but also
data.
for,
Okay. Yeah, with
for the
filter data.
ACSM, if you do some preliminary check, you can get more or less the factors. But of course, if you look closely, if you do more detailed analysis, you can figure out that no, this shouldn't be like this. It's not the ratio of 43 to 44 should be different, or you know, stuff like that. Or you can get like epoxy and stuff. But generally, if you just input stuff without knowing many things, I'm talking about a user that is not experienced, you would get something that's close enough to the truth. While then you need an experienced user to actually get into more detailed information. But basically, this is what I'm asking. How would that work? Yeah, okay.
First of all, I agree with what you say about the factors more or less being right, but not for every instrument. So for the ACSM, I think that what you can get without constraining, if we're speaking about fully unconstrained, ACSM data, fully unconstrained, usual European data, I don't think you will get the factors right. China, the same. Everything is super mixed. Without constraining, it's practically impossible to get it. So for filtered data, I agree. For exact data, I agree. For ACSM, I'm not sure. So this is one thing. But as far as how BAMF would perform in this case and whether it could give you the profiles reasonably, from the test we did for the ACSM, I would say more or less the same as the ACSM, as the PMF, but we have no idea how it would perform in filtered data or the exact data. I also think that I have this bullet in the conclusions about BAMF, but I forgot to mention it. So we have no idea how it works. Maybe it works well, maybe it doesn't. Based on the evidence we have so far, we assume that it should work at least comparably well, but we do not know. So I cannot fully answer to that. If we focus on the ACSM, I would say that for normal data, as far as factor go, there is no obvious advantage of PMF over BAMF. So I'm not sure if I answered your question.
Yes, very much. Thank you.
Awesome.
So, other questions? Okay, if we don't have any other questions, we have to thank Manos for this talk on source apportionment, and maybe Nikos can tell us about the next seminars.
Okay, next seminars, no idea yet. We will see. We'll announce it soon. But before leaving, my warmest wishes on behalf of the HAR to everybody for Easter, for the Greek, for the Orthodox Easter. And we wish you the best for you and your families and your beloved. And looking forward to see you in a month from now.
Καλό Πάσχα.
Καλό
Καλό
Πάσχα.
Πάσχα.
Thank you.
Επίσης σε όλους.
Πάσχα.
Ευχαριστούμε.
Ευχαριστούμε.
Γεια σας, καλό Πάσχα.
Γεια σας.
Yes.
Πολύ καλή, Μάνο.
Σας ευχαριστώ.
Μπράβο, Μάνο.
Ευχαριστώ. Γεια σας, καλή
Τίποτα και
γιορτή.
στο λαό του Παναθηναϊκού.
Γεια σας.
Δημήτρη, πού είσαι? Στη θύρα 13 είσαι?
Ναι, είμαι στη Λεωφόρο, περιμένω τη μικρή να τελειώσει την προπόνηση.
Μεγάλος Παναθηναϊκός, δεν πεθαίνει με τίποτα.
Κύριε
Άντε και στο
Ελευθεριάδου,
Final
βλέπετε,
Four.
κοιτάξτε εδώ.
Και στο
Κοιτάξτε το
Final
πλάνο.
Four.
Ιστορικό να δούμε πότε θα γίνει το καινούργιο για να τον κρεμίσουμε.
Ναι, μην το γκρεμίσετε σαν